I welcome everyone. In this video, we are going to discuss about the correlation between time and frequency response. We know that time response and parameters like time domain specifications. The parameters are delay time, peak time, maximum overshoot, settling time. If we want to control a system by means of time domain response, we are going to take action. You may need to calculate these time domain specifications. This is fully depends upon the eta damping ratio and the damping frequency and the damping natural frequency. These are all the time domain specifications or time domain parameters or time response analysis parameters. We also know that the frequency domain specifications are resonant peak, resonant frequency, bandwidth, cutoff rate, gain margin, phase margin. See, these are all the various parameters related with frequency domain analysis or frequency response analysis. A system can be controlled in closed loop operation either in time response analysis, either with the help of time response parameters or frequency response parameters. It may be controlled. What is the relationship between the time domain specifications and frequency domain specification? This is very important topic to be discussed. The relation between the time domain specification and frequency domain specification. If you want to understand the relationship between these two terms, you need to start from the standard second order closed loop response. C of s divided by R of s is equal to omega n square divided by s square plus 2 eta omega n s plus omega n square. We know that we are assuming that every system is second order system. Okay, it is, which means we are saying that every system is having minimum order as 2, so that we are starting from the standard second order system response equation. Now if you want to, we will solve frequency domain specifications, so that you need to substitute s equal to j omega in that equation. So C of j omega divided by R of j omega, that is equal to T of j omega, say it is T, closed loop response, that is equal to omega n square divided by j omega whole square plus 2 eta omega n j omega plus omega n square. So it will be equivalent to this term minus 1, j square equal to minus 1. So we will take omega n square as common. Okay, we will take the omega n square as common in denominator term. We will have this term, okay, 1 plus 2 eta j omega by omega n minus of omega by omega n whole square. Okay, so this omega n square get cancelled. We will have this equation. In simply we can call it as T of j omega is equal to 1 over 1 minus u square plus 2 j 2 eta u. U is nothing but omega by omega n, that is normalized frequency. Okay, if you are finding the magnitude and as well as the alpha for this closed loop transfer function, we know that the magnitude, that is equal to, if you are having the equation like this, a plus ip, means magnitude will be whole root of a square plus b square. Similarly, phase is equal to tan inverse of b by a. Okay, so this is the standard formula. With the help of this formula, we can also write the magnitude as 1 by whole root of 1 minus u square whole square plus 2 eta u whole square, and also tan inverse of 2 eta u divided by 1 minus u square. This is the phase and magnitude values of this closed loop frequency response. So if you are plotting the magnitude value with respect to the normalized frequency, the graph will look like this. And also if you are plotting the phase value with respect to the normalized frequency, the curve will look like this. Okay, so this is having excuse me, this is having the resonant peak MR value here. Okay, MR value is here, which is the peak value. Okay, if you are plotting this graph is having the peak value here, which is called as MR, resonant peak. Okay, the formula for resonant peak is given here, 1 over 2 eta root of 1 minus eta square. Okay, if eta value is less than 0.707, it is having some peak value. Okay, if the eta value is greater than 0.707, means it is not having any peak value. Okay, at initial stage it is having the maximum value, afterwards it is start decreasing. Okay, there are two cases are there. See, this 0.707 is very important parameter. Okay, important value. Okay, this is the designing parameter. Okay, so up to this value of eta only we can able to find the relationship between time domain and frequency domain analysis. Okay, we will see in later. Anyway, there are two curves. These two curves are representing that if you are setting your damping ratio value less than 0.707, means the system is having some resonant peak, or otherwise it is not having the resonant peak, it is start decreasing continuously. Okay, so this is the inference of this particular graph, and this is the phase plot. Okay, so this is also having some droop characteristics where the eta is equal to eta 1, which is greater than less than 0.707, and it is having the minus 90 degree phase lag at exactly at 1 normalized frequency. Okay, this is the simple plots of, these are all the magnitude and phase plot of closed loop frequency response. Okay, so this is the resonant frequency formula. Okay, so the frequency, resonant frequency is equal to omega n into 1 minus 2 eta square. Then with the help of this formula, with the help of this graph, we can able to decide if eta is 0. Just assume that eta is 0, means MR will be maximum. Substitute eta equal to 0 here. Okay, 1 by 0 is infinity, am I right? So if you are setting your eta damping ratio as 0, means there will be infinite resonant peak. Similarly, if you are setting the eta is 0, means the resonant frequency is equal to natural frequency, am I right? Root of 1 minus 2 eta square. If you are making this term as 0, means omega r equal to omega n. Okay, so, and also we know that in time domain analysis we are having one parameter called maximum overshoot. Okay, if suppose maximum overshoot is eta is 0, means substitute eta is 0 here, e power minus 0 is 1 actually. Okay, so this is the these are all the values. Okay, according to the damping ratio value is 0, resonant peak will be infinity, maximum overshoot will be 1. Okay, if you take one system, okay, you take one system and make the damping ratio as 0, find the resonant peak, it will be infinity. Find the maximum overshoot, it will be 1. Okay, this is the correlation between. So damping ratio is the common parameter for whom? Time response analysis and frequency response analysis. Are you able to understand? Damping ratio is the common parameter, okay, who is being in between time response analysis and frequency response analysis. Okay, so that if you are plotting the curve between MR and eta, resonant peak versus eta, and then maximum overshoot versus eta. Okay, there are two curves are there. First one, this is MR. We told that if eta equal to 0, there will be a infinity amount of MR will be there. So in MR is started to plot from infinite value. Okay, for the sake of simplicity, the curve is shown as starting here. Okay, so at eta equal to 0, MR will be infinity. At the same time, at eta equal to 0, MP will be 1. Am I right? So there will be a correlation between, see, if eta equal to 0, mr will be 1, mp will be infinity. Okay, so sorry, I have mistakenly given, alternately I have given, sorry. So this is the relationship between time domain analysis and frequency domain analysis. Okay, so this is equal to this one. Okay, so if you are setting the damping ratio as 0, means mp will be 1 and mr will be infinity. Am I right? So if exactly if you are setting the eta value 0 to 0.707, okay, you can see that 0 to 0.707 there will be some relationship between mr and mp, that is not both uh, which these two parameters mr and mp are not equal, but there is some linear relationship between both of them, mr equal to k into mp. Okay, so this is the relationship between the time domain specification and frequency domain specification. Okay, so mr is nothing but frequency domain specification, mp is nothing but time domain specification. Am I right? So if you are setting the damping, I told you, right, damping ratio is a common parameter between mr and mp, sorry, time domain and frequency domain analysis. So eta value starting from 0 to 0.707, in this range mr is having the linear relationship with mp. Okay, if you are finding mp, you can also calculate the value of mr. If you are finding mr, you can also find the value of mp, but this relationship will appear only for the duration of 0 to 0.707 eta. If suppose eta value is going beyond 0.707, means you are not able to find any relationship between mr and mp, both are unequal. Okay, you cannot predict the value of mr mp after the damping ratio value going beyond 0.707. Okay, and also there will be a relationship between this ratio omega r by omega d. Omega r is nothing but resonant frequency, omega d is nothing but damping frequency. So if you are plotting this omega r by omega d to eta value, means the graph will look like this. Okay, so if eta equal to 0, means the curve is having the maximum value. Am I right? For the eta value equal to 0, the curve is having the maximum value. Okay, and then we know that delta eta, if you are setting damping ratio as 0, means this is undamped system. Okay, so this variation will be maximum, means there will be a maximum damping oscillations will be there. Okay, so if you are setting eta is equal to 0.707 exactly, means the curve will reach the minimum value. Okay, so which means there is some limited oscillation is there. Okay, so we can conclude that there will be a relationship between time domain analysis and frequency domain analysis only if you are setting the damping ratio between 0 to 0.707. 0.707 is nothing but 1 by root 2. Okay, so between the values 0 to 0.707 of damping ratio, okay, if you are setting your damping ratio between 0 to 0.707, you can find a relationship between time domain and frequency domain analysis. Okay, with the help of mp you can calculate mr, with the help of mr2 you can calculate mp. Okay, there will be some relationship. Okay, so during this period you can see the green color region, time and frequency domain parameters are same. Okay, are same means I am telling that there is some good relationship is there. But if you are changing the damping frequency beyond 0.707 or beyond 1 by root 2, time and frequency domain parameters are not same. Okay, so this is the very important thing. Okay, so what is the purpose of finding this relationship? Okay, that is very important discussion here. There is some necessities there, because if you are having damping ratio as 0.5, Okay, so 0.5 means this green color region, am I right? So you can also calculate the frequency domain parameters from time domain parameters, because both are having some relationship, is it not? So if you want to design your system with more stability, means you can do analysis in both time and frequency domain parameters, so the system will be having more stability. Okay, so if you are setting your damping ratio more than 0.707, it is nearly zero point 0.9, means there will not be a relationship between time domain and frequency domain analysis. You need to separately design based on time domain analysis, and you need to go for a separate design for frequency domain analysis. That is a tedious process. Okay, there are two different analysis you need to do for a single system, means it will take more amount of time. Okay, so if you want to make it as simple, what you have to do is you have to set the damping ratio less than 0.707. Okay, and then do time domain analysis. Okay, with the help of time domain parameters you can also calculate the frequency parameters, am I right? So with the help of that frequency domain parameters you can also do some frequency domain analysis, frequency response analysis also you can do. Okay, so you should know that the range of that relationship is, damping ratios range of relationship is 0 to 0.707. Okay, this is the correlation is relationship. Okay, this is the correlation between time and frequency response analysis.